Okay, now we'll have a look at punchy shear resistance of slabs. So the basic requirement is when you apply a concentrated load on a slab, as in the case of a pad footing, there can be two types of failures as far as punchy shear is concerned. One is, directly under the load, you can get compression induced due to shear, causing crushing of concrete. The other one is, we can define a perimeter, critical perimeter, around the concentrated load, and then there you can get the concrete failure due to tension. So we have to ensure that both these failures cannot happen, and whatever the lower value will govern the carrying capacity in punching shear. So if we first look at the normal failure at a critical perimeter, that will depend on the shear carrying capacity of concrete, and the shear carrying capacity of concrete is given by this equation that you have already seen earlier, and we can easily calculate, and we also learned that it depends on the depth as well. But in case of a slab, not like a beam, we get different reinforcement arrangement in X and Y directions. Two perpendicular directions, different reinforcement can be there. So because of that reason, we consider the average value based on this equation. So we multiply these two and take the square root, and that is the reinforcement in Y direction and Z direction, because in this particular code X direction is considered perpendicular to the member, and so that's why you get PLY and PLZ. So Y and Z directions means the two directions perpendicular to each other on the slab. So you have to see what is the reinforcement in one direction, what is the reinforcement in the perpendicular direction, find the ratios, and from that you can work out rho 1. And then you also have to make sure, if the reinforcement ratio is more than 2%, we cannot have any increase in shear capacity. So the maximum value for reinforcement, whatever the reinforcement you have provided for this calculation, what you use is 2% or 0.02 or 2%. So this is the grade of concrete. K value depends on the depth between 1 and 2, and CRDC is given by this equation, 0.018 divided by gamma C, and that is 0.018 divided by 1.5, which gives a value of 0.12. This gives a value of 0.12. From that, we can work out the carrying capacity of concrete. The shear carrying capacity of concrete can be worked out. So that is the shear carrying capacity of concrete. And then we also have to work out the effective perimeter on which we are going to do the checking. And the perimeter is at 2D, 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 and 2D, and here also circular. And also, when you are considering this D, we generally consider the average value of depth to the reinforcement, because we have reinforcement in two perpendicular directions, so we use the average value. So this is the control perimeter, and the shape of the member can be rectangular, circular, or even T-shaped. And this is a common shape that you might encounter in pad footings. If the column is this shape, then still you can design the pad footing because the control perimeter is given. So that is the basic information. And then we look at an example. So if you have a concentrated load acting on a slab, we can get one failure around this, that is due to the crushing of concrete. And we can get another failure here on this control perimeter, and that is due to the shear capacity of concrete limited by the tension carrying capacity of concrete. So when you want to do the calculation, we always have to find this perimeter, and the effective depth is known, that is the average value. And so we look at an example so that we can easily see what to do. And a slab 175 millimeter thickness. Generally, if the slab thickness is less than 200 millimeters, we don't provide any punching shear reinforcement. So if the slab thickness is 175 millimeters, we are not going to provide any punching shear reinforcement. Effective depth is 145 millimeters. Constructed with 25 megapascal cylinder strength concrete. Reinforced with 12 bars at 150 centers one way, and 10 bars at 200 meter centers in the other direction. So you can see these ratios are different. Determine the maximum ultimate load that can be carried on an area of 300 by 400 millimeters. So this is a reinforced section. So the basic control perimeter is 2A plus 2B. So that is 2A plus 2B. That will give this. And then 2 pi r, 2 pi multiplied by 2d, 2 pi multiplied by 2d, 2 pi multiplied by 2d. So that is twice a plus b plus 4 pi d, and d is 145, so you get 3222 millimeters. So that is the control perimeter, 3222 millimeters away. And in some calculations, you have to actually determine the area enclosed by this as well, but not in this type of calculation. But when you are calculating when you are dealing with foundations, you have to determine the area enclosed by the perimeter as well. Then when you look at the punchy shear capacity, and it depends on this value of VRDC. And if you are using, we should know the rho value, and the rho value here is rho 1 value is 0.0038. So it is 0.0038. So the value is 0.12. The slab thickness is 175. 200 divided by 175 square root plus 1. You get a value greater than 2. So K is 2. 0.12 multiplied by 2 multiplied by 100 multiplied by 0.0038. The value that is calculated for rho is 0.0038. So the value is 0.0038. 100 multiplied by 0.0038 multiplied by 25 to the power 0.8. So you'll find that the VRDC is equal to 0.507, 0.507, and And if you see the multiplication of these two, you will find that it is equal to 0.507. 0.507 multiplied by the perimeter multiplied by 467190, you'll find that the answer is 237 kilonewtons. The answer is 237. I got 37, but close. Here the answer is obtained as 246. And you'll ask, from where you get these values. Actually, using this particular equation, for grade 30 megapascal concrete, using that equation, and for grade 30 megapascal concrete, you can develop a table for shear resistance. And because the shear resistance depends on the grade of concrete, another table has been prepared. So what you do is, depending on the depth, 200 millimeters, 0.38. So you interpolate and find the shear value. Multiplied by this will give the shear resistance of concrete. So whereas on the other hand, if you want, you can straight away use the basic equation, and the basic equation is this. So if you want, you can use the basic equation, otherwise you can use the table. So in this particular example, table has been used. Otherwise, you can use the basic equation, that is 0.12. Slab thickness is less than 200 millimeters, so K is 2. Rho 1 is the average steel ratio, 0.0038. FCK is 25. So you can find VRDC. And once you multiply this shear carrying capacity of concrete by the perimeter, you can get the value of, you can get the load that can be carried without any failure at the control perimeter. So the perimeter at 2D is called control perimeter. Then we also should find whether there can be any failure just around the load, whether there can be any compression failure around the load. So what we do is, we find this perimeter and multiply it by the maximum load carrying capacity in shear. And the maximum load carrying capacity in shear, the value of VRD max for use in a country may be found in national annex. The recommended value is 0.5 new FCD, and FCD is FCK divided by 1.5. New is 0.6 times 1 minus FCK over 250. 0.5. So this is simple VRD max. So if you want, that means stress. This is a stress. If you want the force, you have to multiply it by the perimeter as well. So it is 0.5 multiplied by the perimeter multiplied by the depth, that will give the shear area, multiplied by new value 0.6 times this, multiplied by FCD FCKO 1.5. So when you do that, the perimeter is twice 300 plus 400, depth is 145, and you can see it can carry 914 kilonewtons without any shear failure around, up to 914 kilonewtons without any shear failure around the load. So 914 is far bigger than 246, so the actual value is governed by the tension induced. So the maximum value is governed by the tension induced failure in punching shear, and that is at the control perimeter. So the maximum load that this can carry with a contact area of 300 by 400 is 246 kilonewtons. So basically, no shear reinforcement, straight away you can check it. The important things are, you use the average steel ratio, and the concrete carrying capacity can come from the equation or from the table. It can come from the equation or from the table. It can come from the equation or from the table. And it can, this is the control perimeter. So those are the important things. Then we look at the situation where the load is much higher and this cannot carry the load. We need reinforcement. We need reinforcement. So we are going to look at the next situation where the load is much higher. Load is much higher than this. So this value is unable to carry the shear, punch shear. So because of that reason, we have to provide punch and shear reinforcement. Now, in addition to these two, there's another important table that I have included here, but I will not be using it here. But that is, when you are finding the reinforcement for flexure, you can, to control the tension-induced cracking to 0.3 millimeters, to control the tension-induced cracking to 0.3 millimeters, two tables are given in Eurocode 2, and these actually obtained from the Institution of Structural Engineers, London, issued a guideline, and these values came from the guideline, but these values are available on EC2 as well. So depending on the stress range, or sustained stress in the steel, you have to decide on a maximum diameter or a spacing. So you cannot have any spacing in a member subjected to bending. To control the crack width to 0.3 millimeters, you have to refer either this table or this table. So if you know the diameter, then either you have to control the diameter or else you have to control the spacing. And it says this or this, but generally you can see the stress range. Depending on the stress range, you can decide on a maximum diameter for a bar, or depending on the stress range, you can decide for a maximum spacing. And to determine the sustained loading, you make use of this particular equation, which says that, when you do the calculations, the stress due to permanent loads will be given by the dead load plus part of the live load. And then to determine the stress due to ultimate loads, you get this one. And to see that, if you are providing more reinforcement than required, then this ratio comes. To see whether there's any moment redistribution, this comes. And this is 500 divided by 1.15. So basically, we will be using this particular table and the equation in a later example on concrete pad footing design. So I have included this particular table, which is important for all the elements. So when you have a beam or a slab, in slabs you have different rules. If the stresses are low, if the stresses are high, then you have to refer to this table. But in beams, you have to refer to this, and pad footings, you have to refer to this table when you are providing the reinforcement, just to make sure that the crack widths remain less than 0.3 millimeters. So now we are going to look at slabs with punch and shear reinforcement. If the reinforcement is needed at the basic control perimeter, it is possible to consider two perimeters. So basically what we do is, first we check at 2D, and then what we do is, if we find that the shear is too high, we need reinforcement, then we have to provide punch and shear reinforcement starting from 0.5D starting close to the column face, not more than 0.5D. So that is the first perimeter on which you will provide reinforcement, shear reinforcement. And then you also have to find the perimeter in which the Punchy shear reinforcement is no longer needed. Within 1.5 meter, 1.5D inside that perimeter, again you have to provide reinforcement. And then in between every 0.75D, you have to provide reinforcement. So if I explain it with a diagram, so if you have a concentrated load, then within 0.5D, less than 0.5D, you have to provide reinforcement. Then you have to find the punch and shear perimeter where shear reinforcement is no longer needed. So this is the shear reinforcement. So your 2D can be somewhere here. And this perimeter can be even outside because 2D is failing. Then within 1.5D of that perimeter, you need one layer of reinforcement. So here you need one layer very close to the load. Here you need another layer. So we need within 1.5D, we need one layer. So here we need one. Within 1.5D of this, we need another. Then every 0.75D, we need a layer of links. And in these areas, the distance between two links can be 1.5 times D. But beyond 2D, see 2D is here. Here the spacing between two links can be 2D. So that's how you provide the reinforcement. So when you have a concentrated load, you can get a number of perimeters of shear, punch and shear reinforcement like this. And so you can get punch and shear reinforcement like that. So the important thing is, if this is the limit that you need, then within 1.5D of that, you can provide the last link. No need to provide a link here. The last link can be within 1.5D. And also within 0.5D of this load, you need to provide a link within 0.5D of that. And then every 0.75D, you have to provide a reinforcement. So you can see if the loads are very high, you can provide punch and shear reinforcement. So you can see punch and shear reinforcement should be provided between not more than 0.5D from the loaded area. And also distance 1.5D inside the control perimeter where shear reinforcement is no longer required. So length of the outer control perimeter is given by this equation. So here you use the carrying capacity of concrete in shear and the depth, and this is the force that you have applied. Then it will give a perimeter. So when you know the perimeter, you can find where this perimeter is located. And then you can work out how to provide the punch and shear reinforcement. So vertical links shall be provided around at least 2 perimeters, not more than 0.75D apart. And when you are providing punch and shear reinforcement also, you have to have at least 2 perimeters 0.75D apart. And link spacing around the perimeter is within 2D of the face of the loaded area. Within 2D of the face of the loaded area. So that means the loaded area and 2D, it should be not more than 1.5 times D, and it is limited to 2D at greater perimeters. And if the slab thickness is greater than 200 only, we'll be providing this reinforcement. And when you look at the reinforcement requirement, now you can see a deviation from the beams. In beams, we ignored the carrying capacity of concrete, whereas here 75% of the carrying capacity of concrete is also considered when calculating the reinforcement requirement. And here this alpha refers to the inclination of the shear link. If the shear links are vertical, then alpha is 90 degrees. So you will get sine alpha as ASW sine 90, which is 1. So then you'll find that there's a possibility to simplify this equation, because in this equation you can see this D and this D will cancel out, but this D and this D will cancel out. So here you get D and D here, so those two will cancel out. And SR is the spacing between two perimeters, which can be 0.75 D. And then and also the other important thing is, here you can't use 500. You had to use the effective design strength of Punchy shear reinforcement, which is given by 250 plus 0.25 times D. 0.25 times D. So this value cannot be 500, but it is less than that for certain D values, but the maximum value is 500. So with vertical links, this can be simplified, as I told you. D and D will cancel out, and you will get an equation like this. And this is the minimum area of reinforcement. And when you look at this, it gives the total area of reinforcement needed on a particular perimeter. It gives the total area of shear reinforcement needed on a particular perimeter. So you'll find that the total area of reinforcement needed on a particular perimeter is given by this equation. And you also have to check the minimum reinforcement requirement for shear. And the minimum reinforcement requirement for shear is given in this particular clause for Punchy shear requirement. And it is given as ASW is equal to this. And then when you look at these two, you can say it's 0.053, and ST is the spacing of links around the perimeter, and SR is the radial spacing of links. So you have to calculate this, and if this is larger than this one, then you have to provide this one, because this gives a minimum reinforcement requirement for shear. So again, you have to be careful. There's a minimum value and a calculated value. And if the minimum value is more, then you have to provide that. And these are the equations given in the code. And you can see ASW minimum is given this way in the code, slightly different. But you can rearrange, because ASW minimum 1.5 sine alpha plus cos alpha. Alpha is 90, means this is 1.5 divided by SR/ST. So SR/ST goes up 0.08 square root of CK over Fy. So you can see it's the same equation, but this is how it's given in the code. This is how you can write it after simplifying it. So let's look at another example, designed with Punchy shear reinforcement. And Punchy shear reinforcement can be needed in foundations, especially in the case of raft foundations and so on, where you get heavy column loads supported by the raft. There's no need to increase the thickness of the raft to carry shear. you can actually provide punching shear reinforcement around the heavy loads transferred onto a rough foundation. So it's important to know how to design the shear reinforcement for punching shear. So another example, 260 millimeter thick slab of 25-30 concrete, reinforced with 12 millimeter high yield bars at 125 centers in each direction, subject to dry environment, and it has to carry a concentrated load of 650 kilonewtons. You can see 65 tons. 65 tons over 300 by 300 section, like a steel column supported by a slab. It's like a steel column supported by a slab. Determine the shear reinforcement required for FYK is equal to 500 newtons per meter squared. So exposure is XC1, dry conditions. So you can use 25 millimeter cover. So if you are using 25 millimeter cover, the average effective depth will be can be considered as 215 millimeters after allowing for 8 millimeter links for shear. For shear links, 8 millimeter has been allocated and 12 millimeter bars in 125 millimeters in each direction. So average effective depth is 260 minus 25 minus 8 minus 12. And the maximum permissible force on the loaded area is important. That is the last calculation we just discussed. That is 0.5 times nu times FCD, and so that value is 0.5. 4 into 300 multiplied by 250 is the depth. So when you calculate this, that is 1161 kilonewtons will be carried without any compression failure by the slab, and we are applying only 650 kilonewtons, which is not a problem. And then we look at the basic control perimeter 2D from the loaded face. So that is 2D is 2 into 215, so 430 millimeters. And so the control perimeter is the size of the column, perimeter of the column plus 4 pi d, so 3902 millimeters. So if we have concrete without shear reinforcement, it can carry a load of UD multiplied by the strength of concrete in shear, and for a bending steel ratio of 0.0042, you can calculate the value of this value, and first we will check the outer perimeter, and sorry, before doing that, now we need another parameter, because here we have to actually calculate the force. Force is 650 kilonewtons. 650 kilonewtons to the power 3 divided by 3902 is the perimeter, divided by 215. So the stress is 0.774, and if you look at the steel ratio 0.0042, and we can actually look at this table, 0.0042, and the slab thickness is 260. So effective depth is 215, somewhere here. So you can see the carrying capacity of concrete is about 0.5 0.6 or something like that, 0.55, somewhere here. The shear on the control perimeter is 0.77 when I calculate that. And that is, you know, the load is 650, perimeter is 3902, and the effective depth is 215. So 650 divided by 3902 divided by 215 multiplied by 1000 is 0.774. So the punching shear stress is 0.774. Punching shear stress is 0.774. And the punching shear capacity is 0.55, around 0.55. That means, you know, this is going to fail. This is going to fail. So now what we have a task. We have to decide where we do not need the punching shear reinforcement. So we have to find the perimeter outside 2D. So what we do is we can write an equation for the perimeter outside the outside 2D. So that is 2 pi times, we say x times d. Rather than saying 2d, we say x times d, so that we can find what is x. And the shear carrying capacity is 0.56 multiplied by 0.94, which is 0.56 multiplied by 0.94 from the table is 0.526. The effective depth is 215. The load is 650. So we need a outer periphery of 5743 millimeters, whereas the perimeter at 2D is 3902. So perimeter at 2D gives a stress of 0.77, which is too much. And if we have a perimeter of 5743, then that perimeter gives the stress that can be resisted by the concrete. The stress that can be resisted by concrete is 0.56 multiplied by 0.94, because that table is for 30 megapascal concrete when we are using 25 megapascal concrete. So the shear carrying capacity can be calculated either using the direct equation or using that table. So here the table has been used. And so basically we need a perimeter of 5743 to limit the stress to this value. But what we have at 2D is only 3902. So that means we have to go beyond that. So then x is equal to 3.36. So if we consider control perimeter 3.36 D away from the face of the load, then it's okay. So we have to actually look at what this means. So we have to look at a perimeter. We have a load of 300 by 300. So the load is 300 by 300. And perimeter 2D away does not give enough perimeter. And a perimeter 3.36 away, we get enough length, enough perimeter. We get enough perimeter. And then within 1.5 D of that, we have to provide the outermost reinforcement. So which means 3.36 minus 1.5 is 1.86 D. 1.86 D we need, at 1.86 D we need the outermost reinforcement. Within 0.5 D we need the innermost reinforcement. And between that, every 0.75 D we have to provide a reinforcement. So This way we can find the boundaries on which we have to provide the reinforcement. So the situation is shear reinforcement should be provided within the zone extending from a distance not greater than 0.5 d and less than 3.36 minus 1.5 d, 1.86 d. So, and they are loaded at 0.75 d apart, and 0.75 is into 215 into 0.75 is approximately 161 millimeters. So we say every 160 millimeters apart, we have to provide a set of links. And so the diameter selected, the location selected are 0.4 d, and 0.4 d plus 0.75 is 1.15 d, plus 0.75 d is 1.9 d. So d is 215, 215 into 0.4 into 0.4 is 86 millimeters. So say 85 millimeters, and 85 plus 160 is 245, plus 160 is approximately 400 millimeters. So we can provide reinforcement at these locations, and 215 into 1.86 is 399 millimeters. So at 400 millimeter, we can provide the outermost reinforcement from the face of the load. So we can have 3 layers of reinforcement: 85, 245 and 400 millimeters from the loaded face. So then we also have to decide what is the spacing on the perimeter. The spacing on the perimeter, the 2D is at 430 and our outermost reinforcement is at 400, which means the maximum spacing between two links is 1.5 times D. So we have to have the spacing of links as at 1.5 times D or 323 millimeter apart. So then we also need to decide what is the minimum, the size of the minimum size of the link, and minimum size of the link is given by as minimum that we calculate, that we looked at earlier. The minimum size of the link is given by this. So which means we get 27.3 millimeters squared, and the area of a 6 millimeter link is 28.5, 28.3. So basically even a 6 millimeter link is okay, but we don't have high yield bars of 6 millimeter. So we have to go with 8 millimeter links. So if you are providing 8 millimeter links at these diameters, then we have to calculate the total area for every perimeter by using this equation. Total area for every perimeter by using this equation. So we can do the calculation actually in a table, but if you want, we can also look at the calculation at different perimeters. So for example, if you look at the perimeter at 0.85 millimeter, or let's say we look at this perimeter at 400 millimeter, and the shear carrying capacity of concrete is 0.526, and the shear force at the perimeter of 400 millimeters is, the shear force is 600, shear force is 650 kilonewtons. Shear force is 650 kilonewtons, and the distance is 400 millimeters. Then the control perimeter is at 2 times 300 plus 300 multiplied plus 2 pi into 400, which comes to 2 into 600 plus 2 into 400. So the perimeter is 3712 millimeters at 400 millimeter. So the perimeter is 2712. So you can substitute in this equation. So SW in the outer perimeter should be greater than VRDS. VRDS is 650 into 10 to the power 3 divided by 215 and for 3712. So you get 650 to the power 3 divided by 215 divided by 3712. Then you get 0.814 newtons per meter squared. So the equation is 0.814 minus 0.75 times 0.526 divided by 1.5 times. Now you have to find this effective value, and the effective value is 250 plus 0.25 into 215, so 303 divided by SR. SR is the spacing between two successive perimeters that we considered 0.75D, and multiplied by the perimeter having 3712. So this way you can calculate the total reinforcement requirement, that is 0.814 minus 0.75 multiplied by 0.526 multiplied by 160 multiplied by 3712 divided by 1.5 divided by 303. So you need 548 millimeters squared of reinforcement provided on the outermost perimeter. On the outermost perimeter, you need 548 millimeters squared of reinforcement. And if we consider the spacing, the area of each link is 50.3 millimeters squared, then you need 548 divided by 50.3. That gives 10.89 links. So when you divide it by the perimeter 3712 divided by 10.89, you can find the spacing of the links divided by 10.89. You will find that the spacing of the links is 340 millimeters, and 215 multiplied by 1.5 also comes to 322 millimeters. So that means 340 is too much, so you may have to provide about 12 links. So if you provide about 12 links, you can end up with a spacing of about 310 millimeters. So you may have to, because there are 3 perimeters, you may have to think about the fixing of reinforcement as well. So you might have to actually look at the perimeter, the spacing. But there's another thing that you have to look at, and that is Now, when you look at perimeter inside D and 2D, when you look at the perimeter inside D and 2D, when you look at the other perimeters, then you will get the reinforcement. Sorry, when you get a stress, a much higher stress. For example, if you select the perimeter at 400 millimeters, we are having perimeters at 285 millimeters. So the perimeter as 85 millimeters is 300 into 4 plus 2 pi into 85. So that gives 300 into 4 plus 2 into 3.14 into 85, 1733. And then what you have to do is, as given here, the perimeter is 1734. And when you look at the stress will be 650 to the power 3 divided by 215 divided by 1733. So you get a stress of 1.74. But then you have to substitute in that this equation again. So then you get 1.74 minus 0.75 times 0.526 divided by 1.5 times. Then you have to again find this effective value and SRU1. And so that way you have to actually complete this table based on to find the spacing. And once you find the spacing, you can propose a suitable number of links to carry the shear. So that's the way you have to actually calculate the punchy shear requirement. So to calculate the punchy shear requirement, the first thing is to decide at which perimeters that you are going to provide it, as done here. So first you have to find the outermost perimeter on which you need you do not need the reinforcement, and within 1.5 D of that perimeter you can decide, you can provide the outermost shear reinforcement. And then you have to also decide the inner location, and then every 0.75 D you have to provide a band of reinforcement. And then you can actually substitute in this equation and find the reinforcement that is needed, and then you can actually calculate the total amount of reinforcement needed. And once you calculate the total amount of reinforcement needed, because the diameter of the reinforcement is known, the area of the reinforcement is known, then you can calculate the number of reinforcement you are going to provide, and based on that you can work out the spacing. So here you can see the spacing has been adjusted to be 125 and 250 so that it can be fixed easily on each perimeter, because the spacing is more or less the same. So the spacing of the link has been adjusted. So here you need 14 links, and 1734 divided by 125 is 13.87 links. So 14 links at 125, whereas the spacing can go up to 323 here, but the spacing has been limited to 250 in this one. So you need 3713 divided by 250, a total of 15 links. So that way you have to actually work out the actual spacing of the link, considering the, the ease of fixing the reinforcement. So basically, when you need punchy shear reinforcement due to a very heavy load that can actually occur in rough foundations and so on, then you have to actually do the calculation this way, because the situation that occur in a rough foundation is exactly the same as in this example. You get a heavy load from a column, and the rough foundation thickness we do not try to increase. The thickness may be 1 or 1.2 meter, but you have to decide the punchy shear reinforcement. And the way that we decide the punchy shear reinforcement is by calculating the load and then calculating the perimeter on which we do not need punchy shear reinforcement any longer. And then we can work out on which perimeter we are going to provide the reinforcement. And because the rough foundation will have a considerable thickness, and most instances you might find that with only 2 perimeters, because the depth is D value is high, with only 2 perimeters, sometimes you might be able to provide the sufficient punchy shear resistance, especially considering the fact that it is having a fairly high thickness. So this is how you will do the calculation. So I use this basic example to show you how to do the calculation for punchy shear reinforcement. And these equations can be obtained directly, as I've shown you. And this particular equation is also obtained from the basic equation given in the code. And this is the equation for minimum reinforcement. So any questions on this? So any questions you'd like to ask?
Sir,
Yeah.
Sir, can you please explain how the arrangement of this shear reinforcement around the column again in a sketch, please?
Yeah. I'll come. Just one moment. Okay, now there's another thing that I want to tell you. Now, when you look at shear, very close to the load, when you look at the shear failure, so I'll look at this way. Now, this D is 2D. D and 2D. D and 2D. Between D and 2D, there's something called enhancement, the enhanced capacity of shear, so which is given by 2D over AV. So in this code, when you look at a perimeter in between within 2D, actually there's a possibility for enhancement. I will check and let you know whether we have to consider that this enhancement also. So when you are calculating the shear links, I think we can consider the enhancement, but I'll check and let you know. Because in foundations we consider this, but whether in the slabs, whether we consider that, I'll check and let you know. But as far as answering your question, we have 300 by 300. So we have one perimeter only. What is the first perimeter? First perimeter is 85 millimeters away. Is that right? And the second perimeter is 160 plus 85. Yes, 245 millimeters away. Third perimeter is 400 millimeters away. So we have three perimeters. So along the perimeter, you get bars going like this. So if you select one direction, so select one here, then the other one will be at a spacing of 125 here. And then the way we have selected it, we have one link here, then the other links are at 250 away. So you find this is 250, also 250, and here 125. So here within this area you get two links. So basically what you find is when you provide the links this way, that at this spacing, then you know in the radial directions you will get links going like this, and what we have to do is provide a link like this. So we provide a link like this where the reinforcement will go here and here. So you have to provide a link like that. So that's why, you know, when we calculated the effective depth, we calculated 25 plus 8 plus 12. So then you will have the reinforcement going this way also. So the way that we provide the link is like that. We have to provide a link like this. So that's why, you know, you have to carefully select this particular spacing, but it will go right around the the concentrated load. Is that okay? Have I
Yes,
answered your question?
yes, sir, it's clear.
It's clear. Right. So the only thing that I want to just check is whether this, because if you look at this particular case, then at a distance 85 millimeters, we have a perimeter of 1733. So U value is 1733, and then to look at the equation. Yes. VRDC is CS is equal to 650 multiplied by 2D over AV, which has a maximum value of 4 times this one, 2D over AV, and that is 2 into 215 into divided by AV. AV is 85. So 2 into 215 divided by 85. So that is 4 times. So divided by 4 multiplied by 1733 by 4 divided. I think the shear enhancement is not considered in this particular calculation. When you are doing this, shear enhancement is not considered. So I will anyway double check that and let you know next time whether we can consider shear enhancement. Actually, when you have a load very close to when you have a shear perimeter very close to a load, then in the British codes, we consider that the shear capacity is enhanced. Whereas in Euro codes, what you do is you reduce the load acting by a similar factor. So only thing is, when you are calculating the reinforcement, whether we can consider that, I will just check. I think it's not. Because if you consider this particular value, VRDS is 653 divided by 1733 divided by 215. So gives a stress of 1.74 minus 0.75 multiplied by 0.56526 divided by 1.5 times. So you get 1.74 minus 0.75 into 0.526, 1.344 divided by 1.5 divided by 200 divided by 303 multiplied by 1733 multiplied by 160. 820 millimeters squared divided by 50.3, then you will end up with 16 bars. So what is provided there? In the first perimeter, we are providing 14 bars. Yeah, that's correct. So you can't consider the shear enhancement. In this calculation, you don't consider the shear enhancement. You simply consider that the shear capacity of concrete remains without any enhancement. The shear capacity of concrete remains without any enhancement. So that's the way you have to consider it. Okay. So basically, one of the doubts that was there was whether you can consider the enhancement of the shear capacity, and it is not considered in this particular equation. So basically you have to directly use this value for all the perimeters as the basic value, and this value will increase because the perimeter is reducing, and then this value will remain same. So that way you can calculate the total area of reinforcement needed. So any other question that you would like to ask? Because we will be needing this particular calculation when you are designing rough foundations. Okay. So shall I stop the lecture there? Okay, so I'll stop the lecture and then upload the recording. So next week also on Saturday we'll meet the same time.